So here's something worth thinking about as you settle in tonight. Right now, inside you, there are roughly 37 trillion cells doing their thing. That's not a rough guess. A team of researchers in 2013 actually sat down and tried to count them, tissue by tissue, organ by organ, and that's the number they came up with. 37 trillion. And every single one of those cells is a little machine. It takes in fuel, it produces waste, it communicates with its neighbors, it makes decisions about when to divide and when to die. You are, in the most literal sense, a biological machine of almost incomprehensible complexity. And for most of human history, when that machine broke down, we had almost no idea how to fix it. That's really what biomedical engineering is about. It's the place where engineering, the discipline of designing, building, and understanding systems, meets the human body. And I think the reason it can feel so confusing, so sprawling and hard to pin down is that it sits at this intersection of so many different fields. You've got mechanical engineering, electrical engineering, chemical engineering, material science, computer science, and then on the other side you've got biology, medicine, physiology, pharmacology, genetics. Biomedical engineering borrows from all of them. It speaks all of their languages. And that's what makes it both fascinating and, honestly, a little overwhelming when you first encounter it. But here's the thing. You don't need to understand all of it at once. And tonight, we're going to take it slow. We're going to walk through how this field came to be, how people figured out, piece by piece, that you could apply the logic of engineering to the messy, wet, complicated reality of living tissue. And we're going to start where it makes sense to start, which is a long, long time ago, before anyone would have used the word biomedical or engineering. Back when the first humans looked at a broken body and thought, I wonder if I can fix that. Because that impulse, that desire to intervene, to repair, to replace what's damaged, that's ancient. We're talking thousands of years. There's a mummy in Cairo from around 950 to 710 BC that was found with a prosthetic toe. Not a cosmetic one, not something added after death for the afterlife. An actual functional prosthetic toe, made of wood and leather, designed to be worn while walking. Researchers at the University of Manchester tested a replica of it in 2011 and found that it genuinely helped people who were missing a big toe walk more naturally in Egyptian-style sandals. Think about that. Nearly 3,000 years ago, someone looked at a person who had lost a toe and thought, I can build something to replace that. They shaped wood, they stitched leather, they fitted it to the body. That is biomedical engineering. They just didn't have a name for it yet. And you find these kinds of early interventions scattered all through ancient history. The Egyptians used honey as a wound dressing, and we now know that honey actually has genuine antimicrobial properties, so they were on to something real. In ancient India, around 600 BC, a surgeon named Sushruta was performing reconstructive surgery on noses. He would take a flap of skin from the forehead, fold it down, and shape it into a new nose, keeping part of the flap still connected to its blood supply, so the tissue would survive. This technique, the forehead flap, is still used in reconstructive surgery today. Sushruta also described over 100 surgical instruments, many of them modeled on the shapes of animal jaws and beaks. He was designing tools specifically shaped for the task of working on human tissue. That's engineering thinking applied to medicine, plain and simple. But for a very long time, these were isolated sparks. Brilliant individuals figuring things out through observation and trial and error, but without a systematic framework for understanding why things worked or didn't work. And the reason for that is pretty straightforward. For most of human history, we didn't really understand how the body worked. You can't engineer solutions for a system you don't understand. And the human body was, for centuries, essentially a black box. That started to change during the Renaissance, and the person who probably did more than anyone to crack that box open was Andreas Vesalius. He was born in Brussels in 1514 into a family of physicians, and from a very young age, he was obsessed with anatomy. The story goes that as a boy, he would dissect mice, cats, dogs, anything he could get his hands on. He studied medicine at the University of Paris and then at the University of Padua, and by the time he was 23 years old, he was appointed professor of surgery and anatomy at Padua. 23. And almost immediately, he started doing something that was considered radical at the time. He performed dissections himself. Now, that might sound obvious, but here's the context. For over 1,000 years, European medicine had been dominated by the teachings of Galen, a Greek physician who lived in the 2nd century AD. Galen had written extensively about human anatomy, and his texts were treated as essentially sacred, the final word. The problem was that Galen had never actually dissected a human body. Dissection of humans was forbidden in his time and place, so he worked with animals, monkeys, pigs, goats, and extrapolated to humans. And he got a lot of things wrong. He thought the liver had 5 lobes. He thought the human jawbone was made of 2 pieces, like a dog's. He described a network of blood vessels at the base of the brain, called the rete mirabile, that exists in some animals, but not in humans. And for over 1,000 years, nobody corrected him, because the tradition in medical education was for the professor to sit in a chair high above the dissection table reading from Galen's text, while a barber surgeon did the actual cutting down below. The professor never touched the body. He just read the book. So if what was in the book didn't match what was on the table, well, the book must be right. Maybe this particular body was unusual. Maybe the barber surgeon cut in the wrong place. The text was never questioned. Vesalius changed that. He got down from the chair. He picked up the scalpel himself, and he looked at what was actually there. And what he found was that Galen was wrong. Not about everything, but about a lot of things. Over 200 things, by some counts. And in 1543, when Vesalius was just 28, he published a book called De Humani Corporis Fabrica, on the fabric of the human body. It was 7 volumes. It was illustrated with stunning, detailed engravings, and it was the most accurate description of human anatomy the world had ever seen. The illustrations showed muscles layered over bones, organs in their correct positions, the branching of blood vessels. It was a masterpiece of observation. And here's why this matters for our story. Before you can engineer anything, you need accurate blueprints. You need to know what the system actually looks like, how the parts are arranged, what connects to what. Vesalius gave medicine its first real set of blueprints for the human body. He didn't solve any engineering problems himself. That wasn't his goal. But he made it possible for the people who came after him to start thinking about the body as a system that could be understood in mechanical, structural, physical terms. And that's exactly what started happening. In the decades and centuries after Vesalius, people began applying the tools and concepts of the physical sciences to the body. William Harvey, an English physician, published his theory of blood circulation in 1628. The idea that the heart is a pump, that blood flows in a closed loop, out through the arteries and back through the veins. This was a profoundly engineering-minded insight. Harvey was describing the cardiovascular system as a hydraulic circuit. He even estimated the volume of blood the heart pumps per beat, and used that to argue that the blood must be recirculating, because the body couldn't possibly be producing and consuming that much blood continuously. He did the math. He treated the heart like a mechanical pump and asked, what are the flow rates? What are the volumes? Does this make sense? And once you start thinking about the heart as a pump, a whole world of questions opens up. What's the pressure in the system? How do the vessels handle that pressure? What happens when the pump weakens or when a vessel gets blocked? These are engineering questions. They're the same kinds of questions you'd ask about a water supply system or a hydraulic press. And that's the beautiful, slightly mind-bending thing about biomedical engineering. The body really does operate on principles that engineers already understand. Fluid dynamics, structural mechanics, electrical signaling, feedback control systems. It's all in there. The body just implements these principles using proteins and cells and ions instead of steel and copper and silicon. Let me give you an example that I think really captures this. Your bones, the ones holding you up right now, or rather, the ones you're resting on as you lie there, they're not just static structural beams. They're constantly being remodeled. There are cells called osteoclasts that break down old bone tissue, and cells called osteoblasts that build new bone tissue. And the remarkable thing is that this remodeling process responds to mechanical stress. The places in a bone that experience the most force get reinforced with more material. The places that experience less force get thinned out. It's exactly the same principle that a structural engineer uses when designing a bridge or a building. You put material where the loads are, and you remove material where it's not needed. This principle is sometimes called Wolff's Law, after Julius Wolff, a German anatomist who described it in 1892. But the body was doing it for hundreds of millions of years before Wolff noticed. And that's what makes biomedical engineering so endlessly interesting. You're not just building things for the body. You're studying a system that has already been engineered, in a sense, by evolution. 4 billion years of trial and error, of natural selection, ruthlessly discarding designs that don't work and refining the ones that do. The solutions that evolution has come up with are often staggeringly elegant, but they're also full of compromises, legacy constraints, and outright flaws. Because evolution doesn't design from scratch, it tinkers with what's already there. So you end up with a system that's brilliant in many ways and deeply imperfect in others. And that gap between what the body does well and what it does poorly, that's where biomedical engineering lives. Now, for a long time, the people thinking about these things weren't called biomedical engineers. They were physicians, or natural philosophers, or anatomists, or physiologists. The formal discipline of biomedical engineering didn't really coalesce until the 20th century. But the roots go deep, and the thread that connects Sushruta shaping a nose in ancient India to a modern engineer designing a 3D printed titanium hip implant is the same thread, the conviction that you can understand the body well enough to intervene when it fails, and that you can design and build things that work with living tissue. Speaking of working with living tissue, there's a challenge at the heart of biomedical engineering that makes it fundamentally different from almost every other kind of engineering. And it's worth talking about because it explains so much of what makes this field both difficult and fascinating. When a mechanical engineer designs a bridge, the bridge doesn't fight back, steel doesn't reject the bolts, concrete doesn't mount an immune response against the rebar. But when you put something into a human body, a metal implant, a synthetic material, a transplanted organ. The body notices, and the body has opinions. Your immune system is essentially a security system that has been tuned over millions of years to identify and destroy anything that isn't supposed to be there. Bacteria, viruses, fungi, parasites. The immune system is constantly scanning for foreign invaders and mobilizing responses against them. And it doesn't particularly care whether the foreign object is a dangerous pathogen or a life-saving medical device. If it's not made of your own cells, bearing your own molecular identification markers, the immune system is going to be suspicious of it. And that suspicion can range from mild inflammation, a little redness and swelling around a splinter, say, all the way to a catastrophic rejection response that can destroy a transplanted organ or encapsulate an implant in scar tissue until it's useless. This problem, biocompatibility, the question of how to make materials and devices that the body will tolerate, is one of the great running challenges in the entire history of biomedical engineering. And the story of how people have grappled with it is full of surprises, accidents, brilliant insights, and some genuinely harrowing failures. One of the most important breakthroughs came from a place you might not expect, and it happened almost by accident during the Second World War. There was a young ophthalmologist in the Royal Air Force named Harold Ridley, and he was treating pilots who had been injured when their cockpit canopies shattered during combat. Splinters of the canopy, which was made of a plastic called polymethyl methacrylate, or PMMA. You might know it as plexiglass. These splinters would lodge in the pilot's eyes, and Ridley noticed something remarkable. The splinters just sat there. The eye didn't reject them. There was no significant inflammatory response, no scarring, no encapsulation. The PMMA fragments were simply tolerated. And for an ophthalmologist in the 1940s, that was extraordinary, because the eye is one of the most sensitive, most reactive tissues in the entire body. If you've ever had even a tiny eyelash caught under your lid, you know how aggressively the eye responds to foreign objects. Tears, redness, pain, swelling. The eye wants that thing out. And yet, here were these jagged shards of airplane canopy embedded in the eyes of RAF pilots, and the tissue around them was calm, quiet, almost indifferent. Now, most people would have just noted that as a curiosity and moved on. But Ridley was the kind of person who couldn't let a puzzle like that go. He started thinking, if the eye can tolerate this particular plastic, what else might be possible? And the specific problem he was thinking about was cataracts. A cataract is when the natural lens of your eye, which is normally clear, becomes cloudy over time. It's one of the most common causes of vision loss in the world, and in the 1940s, the only treatment was to surgically remove the clouded lens entirely, which worked in the sense that you got rid of the cataract, but it left the patient without a lens at all. They'd need incredibly thick glasses after surgery, these heavy, distorting lenses that gave everything a kind of fishbowl effect. Not ideal. What Ridley wanted to do was replace the clouded natural lens with an artificial one, an intraocular lens, a tiny, precisely shaped piece of clear material that could sit inside the eye permanently and do the job the natural lens used to do. And here's the thing. The idea was considered almost reckless at the time. The prevailing wisdom in ophthalmology was that you absolutely could not put a foreign object inside the eye and expect it to stay there without causing terrible problems. The eye was too delicate, too reactive. Ridley's own colleagues thought he was frankly a bit mad, but he had those pilots. He had the evidence. He had seen with his own eyes, no pun intended, that PMMA could coexist peacefully with living tissue. So, on November 29, 1949, at St. Thomas's Hospital in London, Harold Ridley performed the first intraocular lens implantation. He placed a tiny disc of PMMA into the eye of a patient whose cataract he had just removed. And it worked. Not perfectly. There were complications. The lens design needed refinement. The surgical technique was rough by modern standards. But the fundamental principle held. The eye tolerated the implant. The patient could see. Think about what that means. Today, cataract surgery with an intraocular lens implant is the most commonly performed surgery in the entire world. Something like 20 million of these procedures happen every year globally, and it all traces back to Harold Ridley looking at shrapnel in a pilot's eye and asking the right question. That's biomedical engineering in a nutshell, honestly. Someone at the intersection of medicine and materials science, paying attention, making a connection that nobody else made, and then having the courage to act on it despite enormous professional resistance. Ridley wasn't fully recognized for his contribution until very late in his life, by the way. He was actually criticized and somewhat marginalized by the ophthalmological establishment for decades. It wasn't until the late 1990s that he received a knighthood, and he died in 2001. But every single person who's had a lens implant, and that's hundreds of millions of people by now, owes something to that observation during the war. Now, PMMA turned out to be a genuinely remarkable material for biomedical applications, but it also opened up a much bigger question, one that researchers are still working on today. Why do some materials provoke an immune response and others don't? What is it about the surface chemistry, the molecular structure, the physical texture of a material that determines whether the body treats it as friend or foe? Because it's not as simple as you might think. It's not just about whether something is toxic or non-toxic. Plenty of non-toxic materials still trigger inflammation. The body's response depends on an incredibly complex interplay of factors: the chemical composition of the surface, the roughness of the surface at a microscopic level, the electrical charge of the surface, how proteins in the blood adsorb onto the material in the first seconds after implantation, and how immune cells interpret those adsorbed proteins. Let me slow down on that for a second, because it's a genuinely fascinating process. The moment you put any material into the body, any material at all, within milliseconds, proteins from the surrounding blood and tissue fluids rush to the surface and coat it. This protein layer forms almost instantly, and it's this layer, not the raw material itself, that the immune system actually encounters first. Your immune cells don't really see the implant directly. They see the protein coat. And depending on the material's surface properties, different proteins will stick to it in different orientations, different densities, different configurations. Some protein arrangements signal danger, foreign object, attack. Others are more neutral. It's like, imagine you moved into a new neighborhood and your neighbors can't actually see you through your walls. All they can see is what your front yard looks like. If your front yard looks familiar and well kept, they relax. If it looks strange and threatening, they call the authorities. The protein layer is the front yard. This understanding didn't come all at once. It developed over decades of painstaking research, starting in the 1960s and 1970s, as biomedical engineers and materials scientists began systematically studying what happens at the interface between synthetic materials and living tissue. And one of the key figures in this story is a man named Robert Langer. Langer is one of those people whose career is so prolific, so wide-ranging, that it's almost hard to summarize. He's an MIT professor, a chemical engineer by training, and he holds more than 1,400 patents. He's been called the most cited engineer in history. But what's interesting about Langer's early career is that it almost didn't happen. When he finished his doctorate in chemical engineering in the early 1970s, all the good jobs for chemical engineers were in the oil industry. That's where the money was. That's where the prestige was. But Langer wasn't interested in oil. He wanted to apply engineering to medicine. And when he started looking for academic positions with that focus, he was rejected. Repeatedly. He applied to major universities and was turned down because the idea of a chemical engineer working on medical problems seemed, at the time, like a strange career choice. People didn't quite know what to do with him. He ended up getting a postdoctoral position in the lab of Judah Folkman at Boston Children's Hospital. Folkman was a surgeon who had a radical theory. He believed that tumors grew by recruiting their own blood supply, a process called angiogenesis, and that if you could block angiogenesis, you could starve tumors. It was a controversial idea in the 1970s, and Folkman needed someone who could figure out how to deliver anti-angiogenic molecules to tumors in a controlled way. That's an engineering problem. How do you get the right amount of a drug to the right place at the right time? And this is where Langer made his first major breakthrough. He developed polymer-based systems for controlled drug release. The idea is beautifully simple in concept, though fiendishly difficult in execution. You take a biocompatible polymer, a material that the body will tolerate, and you embed drug molecules within it. Then you implant this polymer near the site where you want the drug to act. As the polymer slowly degrades in the body, it gradually releases the drug at a controlled, predictable rate. Instead of taking a pill that floods your entire bloodstream with a drug and then wears off, you have a local, sustained release, right where you need it. This was revolutionary. Before Langer's work, the conventional wisdom was that you couldn't release large molecules, proteins, nucleic acids, the kinds of complex biological molecules that are often the most therapeutically interesting, through polymer systems. People thought the molecules were too big, that they'd get trapped in the polymer matrix and never come out, or that they'd be destroyed in the process. Langer showed that it could be done. He published a landmark paper in Nature in 1976, demonstrating controlled release of large molecules from polymer implants, and it changed the entire trajectory of drug delivery as a field. Think about where this leads. Today, controlled drug release systems are everywhere. If you've ever seen one of those long-acting contraceptive implants, a tiny rod that goes under the skin of the arm and releases hormones for 3 to 5 years, that's a direct descendant of Langer's work. Drug-eluting stents, which are little mesh tubes placed inside coronary arteries to keep them open after angioplasty, and which slowly release medication to prevent the artery from re-narrowing. That's controlled release. Chemotherapy wafers that can be placed directly into a brain tumor cavity after surgery, releasing anti-cancer drugs locally for weeks. That's the same principle. The polymer does the work of being a tiny, patient, tireless pharmacist, dispensing exactly the right dose over exactly the right time period. And here's what connects all of this back to the biocompatibility problem we were talking about earlier. Every single one of these systems depends on finding materials that the body won't reject. The polymer has to degrade safely. Its breakdown products have to be non-toxic. The immune system has to tolerate its presence long enough for it to do its job. If the body walls it off in scar tissue too quickly, the drug can't get out. If the body mounts an inflammatory response, you've created a new problem instead of solving one. So the materials, science, and the biology are completely intertwined. You can't do one without the other. And that intertwining That constant conversation between engineering and biology is what pushed the field into increasingly ambitious territory as the 20th century progressed. Because once you've figured out that you can put materials into the body, and once you've figured out that you can use those materials to deliver drugs, the next question is almost inevitable. Can you use materials to build replacement parts? Not just a lens for the eye or a pin for a broken bone, but actual functioning tissues? Can you engineer living structures? That question takes us into one of the most extraordinary chapters in the whole story of biomedical engineering. And it starts with a problem that surgeons had been struggling with for a very long time: the problem of skin. If you've ever had a serious burn, or if you know someone who has, you know that the loss of large areas of skin is one of the most devastating injuries a person can survive. Skin isn't just a wrapper, it's an organ. Actually, it's the largest organ in your body, and it does an astonishing number of things. It keeps water in and bacteria out. It regulates temperature. It senses pressure, pain, heat, and cold. It stretches and heals and renews itself constantly. And when you lose a large area of it, say in a severe burn covering 30 or 40% of the body, the consequences are life-threatening. Infection, dehydration, loss of temperature regulation. Without skin, the body's internal environment is exposed to the outside world, and that's a catastrophe. The body simply cannot cope. And for most of human history, there was almost nothing doctors could do about it. You could dress the wound, try to keep it clean, hope for the best. But large burns were, more often than not, fatal. Even into the 20th century, survival rates for major burns were grim. Now, surgeons did have one tool that worked reasonably well: the skin graft. The basic idea goes back centuries, and we touched on Sushruta earlier, who was reconstructing noses in ancient India using flaps of skin from the forehead. But the modern skin graft, where you take a thin layer of skin from one part of the body and transplant it to the damaged area that really came into its own during the World Wars. Surgeons like Archibald McIndoe, working at Queen Victoria Hospital in East Grinstead, England, during World War II, became incredibly skilled at grafting skin onto burned RAF pilots. And there's a connection to Harold Ridley's story there, because these were the same kinds of patients airmen pulled from burning cockpits. McIndoe pioneered techniques for treating deep facial burns, and his patients, who called themselves the Guinea Pig Club, underwent dozens of surgeries each. The results were often remarkable, given what they'd been through. But here's the fundamental limitation of a skin graft. You're robbing Peter to pay Paul. You're taking healthy skin from one site, called the donor site, and moving it to the burn. That donor site now has to heal on its own, and if the burn is large enough, you simply run out of donor skin. There's not enough healthy skin left on the body to cover the wound, and you can't use someone else's skin, not permanently anyway, because the immune system will reject it, just like it would reject any foreign tissue. Cadaver skin and pig skin can be used as temporary biological dressings, buying time, but they're not permanent solutions. The body recognizes them as foreign and eventually destroys them. So this is the problem that a surgeon named John Burke and an engineer named Ioannis Yannis set out to solve in the late 1970s at Massachusetts General Hospital and MIT, which are right across the river from each other in Boston. And their collaboration is one of those beautiful stories where two very different kinds of expertise come together and produce something neither could have created alone. Burke was a burn surgeon. He spent his days treating patients with devastating injuries, and he understood the clinical problem with painful clarity. Yannis was a materials scientist, a chemical engineer who studied the physical properties of collagen, the protein that forms the structural scaffold of skin and many other tissues. Janos understood polymers, cross-linking, degradation rates, pore sizes. He thought about materials the way an architect thinks about building materials, in terms of structure and function, and how things behave under stress. And here's what they figured out together. Instead of trying to transplant skin from somewhere else, what if you could create a scaffold, a temporary structure, that would guide the body's own cells to regenerate new skin? Not a permanent implant, not a prosthetic, but something more like a trellis for a vine. You put the trellis up, the vine grows along it, and eventually the trellis itself can disappear because the vine is now self-supporting. That's the basic concept, and it sounds simple when you say it like that, but the engineering challenge was enormous. They needed a material that was biocompatible, there's that word again, so the body wouldn't reject it. It needed to be biodegradable, so it would slowly dissolve as the body replaced it with real tissue. The pore size had to be exactly right. Too small, and cells couldn't migrate into the scaffold. Too large, and the cells couldn't get a foothold, couldn't bridge the gaps. The degradation rate had to match the rate of new tissue formation. If the scaffold dissolved too quickly, the wound would collapse before new skin had formed. If it dissolved too slowly, it would interfere with the healing process. Think about how many variables that is. You're trying to engineer a material that talks to the body, that participates in a biological process, that has to get the timing right on a molecular level. What Burke and Janos developed, after years of work, was a bilayer membrane. The bottom layer, the one that would sit against the wound, was made of bovine collagen, collagen from cowhide, combined with a glycosaminoglycan, which is a long sugar molecule found naturally in skin. This collagen gag matrix was carefully cross-linked and had a very specific pore structure, with pores averaging around 20 to 125 micrometers. That's tiny. A human hair is about 70 micrometers across. But it's large enough for fibroblasts, the cells that build connective tissue, to crawl inside and start doing their work. The top layer was a thin sheet of silicone, which served as a temporary substitute for the epidermis, the outermost layer of skin. It kept water in and bacteria out, performing that critical barrier function while the deeper layers regenerated. They called it Integra, and it was first used on patients in the early 1980s. The results were striking. When you place this scaffold on a properly prepared burn wound, the body's own cells would migrate into the collagen matrix, lay down new tissue, and gradually replace the scaffold with something that looked and functioned remarkably like real dermis, the deep, structural layer of skin. After a few weeks, once that new dermis had formed, the silicone layer could be peeled off and replaced with an ultra-thin skin graft, much thinner than what would normally be required, because you'd already rebuilt the foundation. You were no longer asking the graft to do all the work. The scaffold had done the heavy lifting, and this is where I want you to appreciate what a conceptual leap this was. Before Integra, the paradigm in surgery was replacement. Take something out, put something else in. A metal hip, a plastic lens, a transplanted kidney. But Integra was different. It wasn't a replacement. It was a set of instructions. It was a material designed to tell the body what to do, to guide a biological process, and then to vanish. The scaffold itself was temporary. The real product was the tissue the body built. That idea, that you could engineer a material to direct biological regeneration, was revolutionary. It opened up an entirely new way of thinking about medicine, and it gave a name to a field that was just beginning to coalesce. tissue engineering. Now, Integra wasn't perfect. The regenerated skin didn't have hair follicles or sweat glands or the same elasticity as normal skin. It was better than scar tissue, but it wasn't identical to what had been lost. And the process was slow and required careful wound management. But for patients with massive burns who would otherwise have died or been left with crippling contractures, where scar tissue tightens and restricts movement, it was genuinely life-changing. The FDA approved Integra for burn treatment in 1996, and it's still used today, along with newer generations of skin substitutes that have built on Burke and Yannis's original insight. But here's what's really fascinating about the tissue engineering story. It didn't stop at skin. Once people realized that you could use scaffolds to guide tissue regeneration, the question became, what else can we grow? And this is where a few key figures enter the picture, and one name in particular that you'll hear in almost any conversation about tissue engineering: Robert Langer again. We talked about him earlier with the drug delivery work, the controlled release polymers. Well, Langer's lab at MIT became one of the epicenters of tissue engineering research in the 1980s and 90s. He teamed up with a surgeon named Joseph Vacanti from Boston Children's Hospital, and together they articulated a vision that was breathtaking in its ambition. The idea was this: take a biodegradable polymer scaffold, seed it with living cells, the patient's own cells, ideally, and then let biology do the rest. The scaffold provides the shape and the mechanical support. The cells provide the biological function. Over time, the scaffold degrades, and you're left with a living, functioning tissue or organ. Langer and Vacanti published a landmark paper in Science in 1993 that essentially laid out the roadmap for the field, and the range of tissues people started trying to engineer was astonishing: cartilage, bone, blood vessels, heart valves, bladder, liver tissue, nerve guides. Each one presented its own unique challenges because every tissue in the body has a different structure, different mechanical properties, different cell types, different nutritional needs. Engineering cartilage is a completely different problem from engineering a blood vessel, which is a completely different problem from engineering liver tissue. But the underlying philosophy was the same: scaffold, cells, signals. And speaking of signals, this is where growth factors come in. And this is a concept worth sitting with for a moment, because it's central to so much of modern biomedical engineering. Growth factors are proteins that cells use to communicate with each other. They're chemical messages that say things like divide, migrate here, differentiate into this type of cell, build a blood vessel. In normal development and healing, growth factors orchestrate incredibly complex processes. When you cut your finger, a whole cascade of growth factors is released that coordinates the repair, attracting immune cells to fight infection, then fibroblasts to rebuild tissue, then endothelial cells to form new blood vessels. It's a symphony, and the timing and concentration of each signal matters enormously. So tissue engineers realized that just having a scaffold and cells wasn't always enough. Sometimes you needed to add growth factors to the scaffold to give the cells the right instructions. One of the most dramatic examples of this involves bone. Bone has a remarkable ability to heal itself. Set a fracture and it'll knit back together in weeks. But there are situations where the gap is too large or the blood supply is too damaged, and the bone simply can't bridge the gap on its own. For decades, the gold standard for repairing these critical size bone defects was the autograft, taking bone from the patient's own hip, usually the iliac crest, and transplanting it to the defect site. It works well because the transplanted bone brings its own cells and growth factors. But it requires a second surgery, it's painful, and there's a limited supply. In the 1990s, researchers identified a family of growth factors called bone morphogenetic proteins, BMPs, that are the body's own signals for telling stem cells to become bone. BMP2 and BMP7 in particular turned out to be extraordinarily potent. If you put BMP2 on a collagen sponge and implanted it at a bone defect site, new bone would form. No need for a second surgery, no donor site pain. The FDA approved recombinant human BMP2, delivered on a collagen carrier, for spinal fusion in 2002 and for certain fracture repairs shortly after. And for a while, it seemed like a miracle. Surgeons were using it enthusiastically, and the results were often excellent. But here's where the story takes a darker turn, and it's an important one, because it illustrates something fundamental about biomedical engineering. The dose makes the poison. Surgeons started using BMP2 at very high concentrations, sometimes much higher than what had been studied, in clinical trials, and in anatomical locations where it hadn't been thoroughly tested, and complications started appearing. Excessive bone growth in places where you didn't want it, severe swelling, particularly dangerous when used in cervical spine fusions near the airway, inflammatory reactions. There were reports of increased cancer risk, though the data on that remains contested and complicated. What we do know is that a series of studies funded by the manufacturer, Medtronic, initially reported very rosy safety profiles, and it wasn't until independent researchers, notably a group at Yale led by Eugene Karagi, went back and reanalyzed the raw data that the fuller picture of adverse events came into view. Karagi published a series of papers in the Spine Journal in 2011 that essentially argued the complication rate had been dramatically underreported in the industry-sponsored trials. We're talking about adverse event rates that might have been 10 to 50 times higher than what the original publication suggested. And that's not a rounding error. That's a fundamental credibility problem. Now, let that sit for a moment, because this isn't just a story about one product or one company. It's a story about something that runs through all of biomedical engineering, all of medicine really. The tension between enthusiasm and evidence. BMP2 genuinely works. It genuinely helps bone form. The biology is real. But biology doesn't operate like a light switch, where more signal means more of the thing you want. Biology operates in gradients, in contexts, in feedback loops. A growth factor that tells stem cells to become bone at one concentration might trigger runaway inflammation at a higher concentration. A growth factor that works beautifully in the lumbar spine, where there's plenty of room for swelling, might be dangerous in the cervical spine, where even a little extra swelling can compress the airway and become a life-threatening emergency. The molecule didn't change. The context changed, and the dose changed. And that was enough to turn a breakthrough into a cautionary tale. Here's the thing, though, and this is important. BMP2 didn't go away. It's still used. It's still FDA approved. Surgeons just learned, painfully, to be more careful about when and how much. The product label was updated, warnings were added for cervical spine use, and the orthopedic community had a long, uncomfortable reckoning about conflicts of interest in clinical research. Some surgeons who had been enthusiastic advocates had also been receiving significant consulting fees from Medtronic, and that muddied the waters in ways that took years to untangle. But the deeper lesson, the engineering lesson, is about control. In biomedical engineering, you're not just designing a device or a molecule. You're designing an interaction between that device and a living system that has its own agenda, its own regulatory mechanisms, its own capacity to overreact or underreact. And the margin between therapeutic and harmful can be razor thin. Which brings us to something that was happening in parallel during this same era, something that would reshape the entire field of biomedical engineering in ways that are still unfolding right now. And that's the story of the artificial heart. People had been dreaming about replacing the human heart with a machine for a very long time. The heart, after all, is a pump. It's an extraordinary pump. It beats roughly 100,000 times a day, pushes about 2,000 gallons of blood through 60,000 miles of blood vessels, and it does this for decades without maintenance. But conceptually, it's still a pump. And engineers know pumps. So the idea that you could build a mechanical replacement seemed, on the surface, more tractable than growing a new organ from scratch. You don't need to understand every nuance of cardiac biology. You just need to move blood. The early attempts were dramatic and honestly heartbreaking. No pun intended. In 1969, Denton Cooley at the Texas Heart Institute implanted the first total artificial heart into a human patient, a man named Haskell Karp, who was dying of heart failure. The device, designed by Domingo Liotta, was meant to be a temporary bridge, something to keep Karp alive for a few days until a donor heart could be found for transplant. And it did keep him alive for about 64 hours until a donor heart was located and transplanted. But Karp died 32 hours after the transplant. The whole episode was controversial. Michael DeBakey, Cooley's colleague and rival at Baylor, and this was one of the great, bitter rivalries in the history of surgery, accused Cooley of implanting the device without proper authorization, without adequate animal testing, without institutional approval. The fallout was enormous. Cooley was censured by Baylor, he resigned, and the two men didn't speak for decades. They eventually reconciled late in life, but the damage to their relationship and to the broader research program was real. And yet, the dream persisted. In 1982, William DeVries at the University of Utah implanted the Jarvik 7 total artificial heart, designed by Robert Jarvik, though built on years of work by Willem Kolff and his team, into a retired dentist named Barney Clark. This was the first permanent total artificial heart implant, meaning it wasn't a bridge to transplant. It was the destination. Clark lived for 112 days. He was tethered to a massive external pneumatic power console that weighed about 400 pounds. He couldn't leave the hospital. He had seizures, he had bleeding episodes, he had infections. His quality of life was, by most accounts, poor. When he died, the cause was listed as multisystem organ failure and sepsis, but the heart itself had kept beating. Now, think about what that means from an engineering perspective. The pump worked. The mechanical problem was solved, at least in a crude sense. Blood went in, blood went out, pressure was maintained. But the patient still died, because moving blood is only part of what you need to do. You also need to not destroy the blood in the process. You need to not create surfaces where clots form and then break off and travel to the brain, causing strokes. You need to not create entry points for bacteria. You need to not tether the patient to a machine so large they can't live anything resembling a normal life. The engineering challenge wasn't just fluid dynamics. It was biocompatibility. There's that word again. The same fundamental challenge that Harold Ridley faced with his intraocular lens, the same challenge that Burke and Janis grappled with in their skin scaffold. Every time you put something artificial into the body asks the same question. What is this, and should I attack it? For artificial hearts, the blood contact surface was the critical battleground. Blood is exquisitely sensitive to foreign materials. When blood touches a surface that isn't the endothelium, that smooth, living lining of your natural blood vessels, it triggers the clotting cascade. Platelets activate, fibrin forms, and suddenly you've got a thrombus, a clot, growing on the surface of your device. If that clot breaks loose, it becomes an embolus, and if it lodges in a blood vessel in the brain, it causes a stroke. Early artificial heart recipients had terrifyingly high rates of thromboembolic events. They were on aggressive anticoagulation therapy, blood thinners, which reduced the clotting risk but introduced bleeding risk. It was a constant, exhausting balancing act. And then there was hemolysis, the mechanical destruction of red blood cells. If the pump's impeller or valves create too much shear stress on the blood, the red blood cells literally tear apart. Their hemoglobin spills into the plasma. The kidneys have to clear it, and if it's happening fast enough, you get kidney damage, anemia, jaundice. So the engineers had to design pump geometries that moved blood forcefully enough to maintain circulation, but gently enough not to shred the cells. That's a genuinely difficult fluid dynamics problem, and it took decades of refinement to get right. Here's what's really clever about the solution that eventually emerged, and it's a beautiful example of how sometimes the best engineering means rethinking the problem entirely. The early artificial hearts, like the Jarvik 7, were pulsatile. They mimicked the natural heart's squeeze and release rhythm. That made intuitive sense. The natural heart pulses, so the artificial heart should pulse, right? But pulsatile pumps are mechanically complex. They need valves that open and close, membranes or sacs that expand and contract, and all of those moving parts create wear, create surfaces for clot formation, and eventually fail. The Jarvik 7 had 4 mechanical valves. Each one was a potential failure point and a potential site for thrombosis. Starting in the 1990s, engineers began seriously pursuing a radically different approach: continuous flow pumps. Instead of squeezing blood in pulses, these devices use a spinning rotor, essentially a tiny turbine, to push blood in a smooth, continuous stream. Fewer moving parts. In some designs, just one moving part, the rotor itself, suspended by magnetic bearings, so it doesn't even touch the housing, which dramatically reduces wear and blood damage. The HeartMate 2, developed by Thoratec and approved by the FDA in 2008, was a continuous flow left ventricular assist device, an LVAD, that used an axial flow rotary pump about the size of a D battery. It didn't replace the whole heart. It assisted the left ventricle, which does most of the heavy lifting in circulation. And it was a game changer. But here's the wonderfully strange part. If you have a continuous flow LVAD, your blood is moving through your body in a steady stream rather than in pulses, which means you might not have a detectable pulse. A nurse puts a stethoscope on your chest, and instead of lub-dub, they hear a continuous whir. They put a blood pressure cuff on your arm, and they can't get a reading because there's no systolic peak and diastolic trough, just a steady mean pressure. You are alive, your blood is circulating, your organs are perfused. But by the traditional definition of vital signs, you don't have a pulse. It's one of those moments where engineering forces medicine to rethink something it took for granted. What does it mean to have a heartbeat? Is pulsatile flow actually necessary for long-term health? That question, believe it or not, is still being studied. There's some evidence that completely non-pulsatile flow might cause problems over very long periods, changes in vascular tone, issues with the aortic valve that's no longer opening and closing regularly. But for the thousands of patients living with these devices right now, many of them for years, the continuous flow approach has been transformative, and the numbers tell the story. The original pulsatile HeartMate CIF-DVE had a 2-year survival rate of around 24% when used as destination therapy, meaning the patient wasn't expected to get a transplant. The continuous flow HeartMate 2 pushed that to about 58% at 2 years. The latest generation, the HeartMate 3, which uses a centrifugal flow design with a fully magnetically levitated rotor, no contact, no friction, no seals to wear out, has pushed survival even higher and reduced the rates of pump thrombosis and stroke dramatically. Each generation of device represents not just better engineering, but better understanding of how blood interacts with artificial surfaces, how flow patterns affect the vascular system, how to manage the driveline, that cable that exits through the skin to connect to external batteries without it becoming a highway for infection. That driveline, by the way, remains one of the biggest unsolved problems. It's a percutaneous line, meaning it passes through the skin, and the skin never fully seals around it. It's a permanent wound, essentially, and it's a constant infection risk. Patients have to keep the exit site meticulously clean, and driveline infections are one of the most common complications of LVAD therapy. Engineers have been working on transcutaneous energy transfer systems, wireless power transmission through the skin using electromagnetic induction, the same basic principle as wireless phone charging, to eliminate the driveline entirely. Several groups have prototypes. The idea is that you'd wear a coil on the outside of your body, and it would transmit power through your intact skin to a coil implanted underneath, which would charge an internal battery. No hole in the skin, no infection highway, but getting enough power through tissue, reliably, efficiently, and without generating too much heat, because you really don't want to cook the tissue between the coils, has been an engineering challenge that's taken longer to solve than anyone initially expected. And this is where the story of the artificial heart connects to something even broader, something that was emerging in the late 20th century and has since become one of the most transformative forces in all of biomedical engineering. Because the artificial heart, for all its sophistication, is still fundamentally a machine doing a machine's job, moving fluid. But what if you could combine the precision of engineering with the adaptability of living biology? What if, instead of building a pump to replace the heart, you could grow a new heart? That idea, growing organs from a patient's own cells, sounds like science fiction, and for most of history it was. But in the 1990s, a series of experiments began to suggest it might actually be possible. And the story of how those experiments came together involves an unlikely collaboration between a surgeon who refused to accept the limits of transplantation and a polymer chemist who had already changed the rules once before. You might remember Robert Langer, the MIT chemical engineer whose controlled-release polymer work had upended drug delivery. Well, Langer teamed up with a pediatric surgeon at Boston Children's Hospital named Joseph Vacanti, and together they began asking a question that seems almost absurdly ambitious when you say it out loud. Can we build living tissue the way an engineer builds a bridge? Not by waiting for a donor organ, not by implanting a machine, but by constructing biological structures from scratch, scaffolds seeded with cells, shaped into the geometry of an organ and coaxed into becoming functional tissue. And the reason Vacanti was the right person to ask this question is that he spent his days watching Children die on transplant waiting lists. That changes you. That makes you willing to entertain ideas that other people dismiss as fantasy. Vacanti had trained as a transplant surgeon. He knew the mathematics of organ shortage intimately. In the United States alone, thousands of patients were dying every year, waiting for livers, kidneys, hearts. The supply of donor organs was never going to catch up to the demand. It was structurally impossible, because you needed someone else to die in exactly the right way, at exactly the right time, in exactly the right place. And the organ had to be a match, and it had to be harvested and transported and implanted within hours. The whole system was heroic and inadequate at the same time. Vacanti looked at that reality and thought, there has to be another way. And Langer, meanwhile, had spent years thinking about how synthetic materials interact with living cells. His controlled release work had already shown that you could embed biological molecules inside polymer matrices and have them released in a controlled fashion. He understood, at a deep level, how cells respond to their physical and chemical environment, how the texture of a surface, the stiffness of a material, the presence of certain signaling molecules could all influence whether a cell lived or died, whether it multiplied or stayed quiescent, whether it differentiated into one type of tissue or another. So when Vacanti came to him and said, essentially, can we build scaffolds that cells would grow on and turn into organs? Langer didn't laugh. He said, let's figure it out. Their collaboration, which began in the mid-1980s, became one of the most productive partnerships in the history of biomedical engineering, and the landmark moment, the one that put tissue engineering on the map for the general public, was that 1993 paper in Science that we touched on earlier, where they laid out the conceptual framework: scaffold, cells, signals, 3 ingredients. You take a biodegradable scaffold made from something like polyglycolic acid or polylactic acid, materials that the body can safely break down over time, and you shape it into the form you want. Then you seed it with the right type of cells, often taken from the patient themselves. And then you provide the biochemical signals, growth factors, nutrients, mechanical stimulation that tell those cells what to become. In theory, the cells colonize the scaffold, lay down their own extracellular matrix. The scaffold gradually dissolves away, and what you're left with is living tissue in the shape you designed, in theory. Because here's the thing about tissue engineering. The concept is elegant, but the execution is brutally difficult. And the reasons why tell you a lot about the difference between engineering with steel and engineering with biology. Think about what a living tissue actually needs. Every cell in your body needs oxygen and nutrients, and it needs them constantly. Not once a day, not once an hour, but every second. And it needs to get rid of waste products just as constantly. In your body, that job is handled by your vascular system, an incredibly dense network of blood vessels that branches and branches and branches until you get down to capillaries so small that red blood cells have to squeeze through them single file. No cell in your body is more than about 100 to 200 micrometers from the nearest capillary. That's roughly the width of a human hair. If a cell ends up farther away than that from a blood supply, it dies. Simple as that. So when you seed cells onto a scaffold in the lab, the cells on the outer surface do fine. They're in contact with the culture medium. They get oxygen, they get nutrients. But the cells deeper inside the scaffold? They're in trouble. As the tissue grows thicker, the interior becomes a dead zone. Oxygen can't diffuse fast enough. Nutrients can't reach. waste builds up. The cells at the center starve and die, and what you end up with is a thin shell of living tissue around a necrotic core. This is called the vascularization problem, and it has been the single biggest obstacle in tissue engineering for the past 30 years. You can grow skin because skin is thin. You can grow cartilage because cartilage is avascular. It doesn't have blood vessels in it naturally, so cells are already adapted to low oxygen conditions. But growing a thick, metabolically active organ like a liver or a kidney or a heart, you need to solve vascularization first. You need to build the plumbing. And this is where the field has gotten extraordinarily creative. One approach is to seed endothelial cells, the cells that line blood vessels, along with the tissue cells, hoping they'll self-organize into vessel-like networks within the scaffold. And amazingly, they sometimes do. Endothelial cells have this remarkable tendency to find each other and form tube-like structures, almost as if they remember what they're supposed to be doing. But these self-assembled networks are often disorganized, incomplete, and not connected to the host's blood supply when you implant the construct. So researchers have tried pre-vascularizing scaffolds, literally engineering channels into the scaffold that mimic blood vessel networks, then lining those channels with endothelial cells before implanting the whole thing. The idea is that when you put this construct into the body, the host's own blood vessels will connect to the pre-formed channels, and blood will start flowing through the engineered tissue. Some of the most creative work in this space has used three-dimensional printing, bioprinting, as it's called. Instead of casting a scaffold and seeding cells onto it, you print the scaffold and the cells simultaneously, layer by layer, using bioinks that contain living cells suspended in hydrogels. The printer can deposit different cell types in different locations with remarkable precision. You can print a layer of structural cells, then a layer that includes a channel for a future blood vessel, then more structural cells, building up complex architectures that would be impossible to achieve by hand. Groups at Wake Forest University, led by Anthony Atala, have been pioneers in this area. Atala's lab printed a miniature kidney-shaped structure as early as 2002. It wasn't a functional kidney, more of a proof of concept, but it captured the public imagination in a powerful way. More practically, his team has successfully engineered bladders from patients' own cells and implanted them, reporting results in The Lancet in 2006 from patients who had received lab-grown bladders years earlier and were doing well. But let's be honest about where the field actually stands, because there's been a persistent gap between the headlines and the reality. The organs that have been successfully engineered and implanted in humans are, for the most part, relatively simple ones: bladders, tracheas, skin, cartilage. These are organs with simpler structures, lower metabolic demands, or natural avascular properties. The big prizes, a functional liver, a functional kidney, a functional heart, remain out of reach, and the reasons are instructive. Take the kidney. A single human kidney contains about 1 million nephrons. Those are the tiny filtering units that do the actual work of cleaning your blood. Each nephron is an exquisitely complex structure involving multiple distinct cell types arranged in a precise three-dimensional architecture, connected to a blood supply, and organized to create specific pressure gradients that drive filtration. The kidney doesn't just filter blood. It regulates electrolyte balance, controls blood pressure through hormone secretion, manages acid-base balance, activates vitamin D. It's not one organ doing one thing. It's a dozen different functions integrated into a single package. Engineering that from scratch is a problem of staggering complexity. And then there's the heart, which brings us full circle in a way. Remember the artificial heart, the HeartMate, the Jarvik, all those mechanical pumps. The reason those devices exist is precisely because growing a biological replacement heart is so hard. The heart is a thick-walled muscular organ that beats 100,000 times a day, with 4 chambers, 4 valves, its own electrical conduction system, its own coronary blood supply, and a structure that has to withstand enormous mechanical stresses while maintaining precise timing. If you wanted to engineer a heart from a patient's cells, you'd need to solve vascularization at a scale no one has achieved. You'd need billions of cardiomyocytes beating in synchrony, and you'd need the whole thing to hook up to the patient's existing circulatory system and start working immediately. Because unlike a bladder, you can't ease a heart into service. Gradually, it either works or the patient dies. One of the most promising approaches to this problem has been decellularization. The idea is beautifully simple. Instead of building a scaffold from synthetic polymers, you take an actual organ, from a cadaver or from an animal, and you strip away all the living cells, leaving behind just the extracellular matrix. That matrix is the natural scaffold, the structural framework that the cells were living on. It retains the organ's three-dimensional architecture, including the vascular tree, all those branching channels where blood vessels used to be. Then you reseed that natural scaffold with the patient's own cells, hoping they'll repopulate the structure and restore function. Doris Taylor's group at the University of Minnesota demonstrated this with a rat heart in 2008. They took a rat heart, perfused it with detergent solutions that washed away all the cellular material, leaving behind a ghostly, translucent scaffold that still had the shape of a heart, chambers, valves, vascular channels, everything. Then they reseeded it with neonatal cardiac cells and put it in a bioreactor. And after a few days, the reseeded heart began to contract. It was weak, uncoordinated, nothing like a functional heart. But it was beating. Living cells on a natural scaffold, generating contractile force. The paper was published in Nature Medicine, and it was one of those moments where the field collectively held its breath because it suggested that the architecture problem might be solvable, that nature had already built the scaffold, and maybe we just needed to learn how to refurbish it. Since then, decellularization has been applied to larger organs. Researchers have decellularized pig hearts, pig kidneys, pig lungs, even whole human organs from donors deemed unsuitable for transplantation. The scaffolds are stunning. You can hold a decellularized pig kidney in your hand and see the entire vascular tree, branching from the renal artery down to the tiniest capillaries, all preserved in this pale, almost translucent matrix. The challenge, as always, is recellularization. Getting enough cells to repopulate an entire organ, getting them to the right locations, getting them to mature and function. This remains enormously difficult. When you perfuse cells into a decellularized kidney scaffold, they tend to cluster near the entry points rather than distributing evenly throughout the structure. The deeper regions, again, are hard to reach. And even when cells do engraft, getting them to organize into functional nephrons with the right polarity and the right spatial relationships, that's a level of biological self-organization that we can encourage but can't yet reliably control. And this is where another technology enters the story, one that would fundamentally change what biomedical engineers thought was possible, not just for tissue engineering, but for the entire field of medicine. Because around the same time that Taylor was decellularizing rat hearts, a researcher in Kyoto, Japan, was about to announce a discovery that would earn him a Nobel Prize and rewrite the rules of cell biology. His name was Shinya Yamanaka, and what he figured out was how to turn an ordinary adult cell, a skin cell say, back into something that behaves like an embryonic stem cell. The implications for tissue engineering were enormous, and they're still unfolding today. So let's talk about what Yamanaka actually did, because it's one of those discoveries that sounds almost too simple when you describe it, and yet it took decades of accumulated knowledge in developmental biology to even know where to look. The year was 2006. Yamanaka and his postdoctoral researcher Kazutoshi Takahashi published a paper in the journal Cell showing that by introducing just 4 genes into ordinary mouse skin cells, fibroblasts, the most common, most boring cells in your body, they could reprogram those cells into a pluripotent state. Pluripotent meaning they could become essentially any cell type in the body. Heart cells, nerve cells, liver cells, blood cells, you name it. These reprogrammed cells behaved almost identically to embryonic stem cells, the gold standard of cellular flexibility, but they didn't come from embryos. They came from adult tissue. Yamanaka called them induced pluripotent stem cells, or iPSCs, and the name stuck. Now, the 4 genes he used, OCT3/4, SOX2, KLF4, and c-MYC, sometimes called the Yamanaka factors, were all transcription factors, proteins that regulate how other genes are expressed. Think of them as master switches. In an embryonic stem cell, these switches are turned on, keeping the cell in that flexible, undifferentiated state where it hasn't yet committed to becoming any particular cell type. In an adult skin cell, those switches have been turned off. The cell has already made its choice. It's a fibroblast, and, under normal circumstances, it's going to stay a fibroblast forever. What Yamanaka showed was that by forcibly turning those 4 switches back on, you could essentially rewind the developmental clock. You could take a cell that had already specialized and push it back to something like its original, uncommitted state. A year later, in 2007, Yamanaka's group and, independently, James Thompson's group at the University of Wisconsin did the same thing with human cells. Human skin cells, reprogrammed into human iPSCs. And that's when the biomedical world really started paying attention, because the implications were staggering. Here's why this mattered so much for tissue engineering specifically. Remember the fundamental challenge. You need cells, lots of them, the right types, to populate your scaffolds and build functional tissues. Before iPSCs, your options were limited. You could use a patient's own cells, but harvesting enough of the right type was often impractical or impossible. You could use embryonic stem cells, which had incredible flexibility, but came with profound ethical controversies and, crucially, would be immunologically foreign to the patient. Your body would reject them just like it would reject a transplanted organ from a stranger. Or you could use adult stem cells, which exist in various tissues but are rare, hard to isolate, and generally more limited in what they can become. iPSCs changed that equation completely. In theory, and increasingly in practice, you could take a small skin biopsy from a patient, reprogram those skin cells into iPSCs, then direct those iPSCs to become whatever cell type you needed. Cardiomyocytes for a damaged heart, dopaminergic neurons for Parkinson's disease, insulin-producing beta cells for diabetes, retinal pigment epithelium cells for macular degeneration. And because those cells would carry the patient's own DNA, the immune system would recognize them as self. No rejection. No lifelong immunosuppression. It was, at least conceptually, the missing piece that tissue engineering had been waiting for. Yamanaka shared the Nobel Prize in Physiology or Medicine in 2012 with John Gurdon, the British developmental biologist who had shown back in 1962, using frogs, that cell specialization was reversible in principle. Gurdon had taken the nucleus from an adult frog intestinal cell, transplanted it into an egg cell whose own nucleus had been removed, and gotten a viable tadpole. That experiment proved that adult cells still contain all the genetic information needed to build an entire organism. The information isn't lost during development, it's just silenced. Yamanaka's work, 44 years later, showed how to unlock that silenced information with just 4 molecular keys. It's a beautiful arc of scientific discovery, spanning half a century, 2 continents, and 2 very different organisms. But here's the thing about iPSCs that's important to understand. They're not magic. They're powerful, but they come with their own set of challenges that biomedical engineers have been working through ever since. For one, the reprogramming process itself is inefficient. When Yamanaka first did it, only a tiny fraction of the treated cells actually became iPSCs, something like 1 in 1,000 or even fewer. The rest either didn't reprogram at all or died in the attempt. And one of the 4 original Yamanaka factors, c-Myc, is a known oncogene, a gene associated with cancer. Using it to reprogram cells raised immediate concerns about tumor formation. If you're going to put these cells into a patient, you absolutely cannot have them turning cancerous. So a huge amount of work in the years following 2006 focused on making the reprogramming process safer and more efficient. Researchers found ways to deliver the reprogramming factors without permanently inserting them into the cell's DNA using messenger RNA or proteins or small molecules instead of the viral vectors that Yamanaka originally used. They found combinations that didn't require c-Myc. They improved the efficiency, developed better methods for selecting successfully reprogrammed cells, and established rigorous quality control protocols. It's the kind of painstaking, unglamorous optimization work that rarely makes headlines, but is absolutely essential for turning a laboratory discovery into something clinically useful. And this is actually a pattern you see over and over in biomedical engineering, right? The breakthrough gets the Nobel Prize, the front page coverage, the breathless headlines about how everything is about to change. And then there are 10, 15, 20 years of quiet, determined work by hundreds of researchers figuring out how to make it actually work in real patients. The gap between proof of concept and clinical reality is enormous, and it's filled with engineering problems, process engineering, quality control, manufacturing, scale-up, regulatory navigation. It's not as romantic as the eureka moment, but it's where the real medicine gets made. Now, one of the most advanced clinical applications of iPSC technology is happening in Japan, which makes sense given that it's Yamanaka's home country and the Japanese government invested heavily in iPSC research after his discovery. In 2014, a team led by Masayo Takahashi, no relation to Yamanaka's collaborator Kazutoshi Takahashi, at the Riken Center for Developmental Biology, performed the first clinical procedure using iPSC-derived cells. The patient was a woman in her 70s with age-related macular degeneration, a condition where the retinal pigment epithelium, a thin layer of cells at the back of the eye that supports the photoreceptors, deteriorates, leading to progressive vision loss. Takahashi's team took skin cells from the patient, reprogrammed them into iPSCs, differentiated those iPSCs into retinal pigment epithelium cells, grew them into a thin sheet, and surgically implanted that sheet under the patient's retina. The eye, it turns out, is a particularly good place to start with cell therapies. It's small, so you don't need billions of cells. It's relatively immune privileged, meaning the immune system is less aggressive there than in other parts of the body. and you can directly observe what's happening. Ophthalmologists can literally look through the pupil and see how the transplanted cells are doing. The procedure went well. The implanted cell sheet survived. The patient's vision stabilized. It wasn't a cure, the disease didn't reverse, but the degeneration stopped progressing, and that was remarkable. There was actually a complication with the second planned patient in that trial. Genetic mutations were found in the iPSCs during quality control screening, and the transplant was called off. Which, honestly, is the system working as it should? You screen, you find a problem, you stop. But it highlighted one of the ongoing concerns with iPSC technology. The reprogramming process can introduce genetic changes, and every batch of cells needs to be carefully checked before it goes anywhere near a patient. Since then, clinical trials using iPSC-derived cells have expanded, though cautiously. There are trials for Parkinson's disease, where iPSC-derived dopaminergic neurons are being transplanted into patients' brains. Jun Takahashi, yet another Takahashi, and also at Kyoto University, has been leading that work. There are trials for heart failure, where sheets of iPSC-derived cardiomyocytes are being placed on damaged heart tissue. There are trials for spinal cord injury, for corneal disease, for blood disorders. Each one is early stage, each one is small, and each one is being watched with a mixture of hope and caution by the broader medical community. But let's zoom out for a moment, because iPSCs didn't just matter for tissue engineering. They opened up an entirely different avenue that has arguably had even more impact so far: disease modeling. Think about what it means to have iPSCs from a patient with a genetic disease. You can take skin cells from someone with, say, amyotrophic lateral sclerosis, ALS, Lou Gehrig's disease, reprogram those cells into iPSCs, and then differentiate them into motor neurons, the exact cell type that's dying in that patient's body. Now you have motor neurons in a dish that carry the patient's specific genetic mutation. You can watch them develop, watch them degenerate, study what goes wrong at the molecular level. You can test drugs on them. You can compare them to healthy motor neurons derived from a control donor and look for differences. Before iPSCs, if you wanted to study a human disease at the cellular level, your options were limited. You could study animal models, but a mouse with an engineered genetic mutation doesn't always recapitulate what happens in a human. You could study cells from post-mortem tissue, but those cells are dead and represent only the end stage of the disease. You could study cell lines, immortalized cells that grow indefinitely in culture, but those are often cancer-derived and behave very differently from normal cells. iPSCs gave researchers something they'd never had before: a renewable, patient-specific source of virtually any human cell type, carrying that patient's exact genetic background. It was like getting a window into the disease while it was still happening, at the cellular level, in a dish on your lab bench. And this connects to something even broader that's been transforming biomedical engineering over the past decade or so: the concept of organs on chips. Because once you can make any cell type from iPSCs, the next question becomes, can you arrange those cells into something that mimics the architecture and function of an actual organ at a small scale, well enough to use it for drug testing? And this is where the work of Don Ingber at Harvard really comes into focus. Ingber is a fascinating figure, trained as both a physician and a cell biologist, and deeply influenced by the architect Buckminster Fuller, the guy who popularized geodesic domes. Ingber spent years studying how cells respond to mechanical forces, how the physical structure of their environment shapes their behavior. And that insight that cells don't just care about chemistry, they care about physics, about the push and pull of the world around them, became the foundation for something genuinely revolutionary. Here's the basic idea behind an organ on a chip. You take a small piece of clear, flexible polymer, usually something called PDMS, polydimethyl siloxane, which is essentially a type of silicone, and you mold tiny channels into it. We're talking channels that might be the width of a human hair, sometimes a bit wider. Then you line those channels with living human cells. But here's what makes it more than just cells in a tube. You can create multiple channels separated by a thin, porous membrane, and you can put different cell types on each side. You can flow air through one channel and liquid through the other. You can stretch the membrane rhythmically to mimic breathing. You can apply fluid shear stress to mimic blood flow. What you end up with is not an organ. It's far too small for that. But it's a tiny, functional unit that recapitulates key aspects of how an organ actually behaves. Ingber's team published their landmark Lung on a Chip in Science in 2010. They had a channel lined with human lung alveolar epithelial cells on one side of a membrane and human pulmonary capillary endothelial cells on the other side. Air flowed over the lung cells. Nutrient medium flowed past the blood vessel cells, and the whole membrane stretched and relaxed cyclically, mimicking the mechanical motion of breathing. What they found was remarkable. This tiny device reproduced responses that you'd normally only see in a living lung. When they introduced bacteria to the air side, the immune cells on the blood side migrated across the membrane to attack them, just like they would in your actual lungs. When they introduced certain nanoparticles, the device showed inflammatory responses and toxicity patterns that matched what had been observed in animal studies, and crucially, in some human clinical data, patterns that traditional cell cultures grown flat on a plastic dish completely missed. Think about what that means for a second. For decades, the standard way to test whether a drug was safe or effective was a pipeline that went something like this. First, you test the drug on cells in a dish. Then, you test it in animals, usually mice, sometimes rats, sometimes larger animals. If it passes those hurdles, you move to human clinical trials, which are enormously expensive and take years. And here's the uncomfortable truth about that pipeline. It fails constantly. Something like 90% of drugs that make it through animal testing go on to fail in human trials. 90%. That's a staggering waste of time, money, and, if we're being honest, animal lives. And the reason for that failure rate is pretty straightforward. Mice are not people. A mouse liver metabolizes drugs differently than a human liver. A mouse immune system responds differently than a human immune system. The biology is similar enough to be useful, but different enough to be misleading in critical ways. Organs on chips offered a potential way to close that gap. Instead of testing drugs on mouse cells or mouse organs, you could test them on human cells arranged in architectures that mimic human organ function. And when you combine that with iPSC technology, when you can derive those cells from a specific patient's skin or blood, now you're not just testing on generic human cells. You're testing on cells that carry a particular person's genetic background. You could, in principle, build a panel of liver chips using cells derived from people with different genetic variants of drug metabolizing enzymes and predict which patients would have adverse reactions to a medication before anyone swallows a single pill. Ingber's group at the Weiss Institute at Harvard went on to build chips for multiple organs: lung, intestine, kidney, liver, bone marrow, skin, blood-brain barrier. And then they did something even more ambitious. They started linking chips together. A liver chip connected to a kidney chip connected to an intestine chip, with fluid flowing between them like a simplified circulatory system. The idea is sometimes called body on a chip or human body on a chip, and it's an attempt to model how drugs move through and affect multiple organ systems simultaneously. Because that's how drugs actually work in your body, right? You swallow a pill, it gets absorbed in your gut, metabolized in your liver, filtered by your kidneys, and along the way, it might affect your heart, your brain, your immune system. A single organ chip can't capture those interactions, but linked chips start to approximate them. Now, I should be honest, this technology is still maturing. As of the early 2020s, organs on chips haven't replaced animal testing. The FDA has been genuinely interested, and in 2022, the FDA Modernization Act was signed into law in the United States, which for the first time removed the requirement that drugs must be tested on animals before human trials. That doesn't mean animal testing is over. It means the door is now open for alternative methods, including organs on chips, to be used instead. It's a significant policy shift, and it happened in part because the technology had reached a point where regulators could see a credible path forward. And this is where something really interesting happens in the story of biomedical engineering. All these threads we've been following start to converge. You've got biomaterials, the descendants of Harold Ridley's accidental discovery about PMMA, now engineered at the molecular level to interact with cells in precisely controlled ways. You've got tissue engineering scaffolds, the intellectual grandchildren of Burke and Janus's collagen GAG matrix, now being three-dimensionally printed with exquisite control. You've got iPSCs, Yamanaka's gift to the field, providing patient-specific cells of virtually any type. And you've got microfluidic engineering, borrowed from the semiconductor industry, enabling the construction of these tiny organ-mimicking devices. Each of these threads developed somewhat independently, driven by different people solving different problems, but they're all feeding into the same grand ambition: to understand and repair the human body at a level of precision that would have seemed like science fiction 50 years ago. Let me give you a concrete example of how these threads weave together in modern practice. Consider the problem of liver disease. Your liver is an astonishing organ. It performs over 500 distinct functions, from metabolizing drugs to producing bile, to synthesizing proteins, to filtering toxins from your blood. It's also one of the few organs in the adult body that can regenerate. You can lose up to 70% of your liver, and it will grow back. But when the liver fails, from chronic hepatitis, alcoholism, fatty liver disease, genetic conditions, it fails catastrophically. And right now, the only definitive treatment is a transplant. And there aren't nearly enough donor livers to go around. So researchers have been attacking this problem from multiple angles simultaneously. Some groups are working on liver-on-a-chip platforms to better understand liver disease and test potential drugs. Others are using decellularization. Remember that technique where you wash away all the cells from a donor organ, leaving just the extracellular matrix scaffold? To create liver scaffolds that could potentially be repopulated with a patient's own iPSC-derived liver cells. Others still are working on bioprinting liver tissue, trying to solve the vascularization problem that has haunted tissue engineering since the beginning because the liver has an incredibly complex dual blood supply. It receives oxygenated blood from the hepatic artery and nutrient-rich blood from the portal vein, and those two supplies mix in tiny structures called sinusoids that are lined with specialized cells. Nobody has built a fully functional bioengineered liver yet, but the progress is real and measurable. In 2013, Takanori Takebe at Yokohama City University in Japan reported growing tiny liver buds. They called them liver organoids, from iPSC-derived cells. And when they transplanted these liver buds into mice, the buds connected to the mouse's blood supply and began performing liver functions. It was a proof of concept, not a cure, but it demonstrated that iPSC-derived liver cells could self-organize into functional tissue in a living body. And this idea of organoids, that's another thread worth pulling on for a moment. An organoid is essentially a miniature, simplified version of an organ grown in a dish. You take stem cells, often iPSCs, and you provide them with the right cocktail of signaling molecules, and something almost magical happens. The cells self-organize. They differentiate into multiple cell types. They arrange themselves into three-dimensional structures that resemble the architecture of the real organ. Brain organoids form layered structures reminiscent of the cerebral cortex. Intestinal organoids form crypt and villus structures, like the lining of your gut. Kidney organoids develop nephron-like tubules. The pioneering work on intestinal organoids came from Hans Clevers at the Hubrecht Institute in the Netherlands, starting around 2009. Clevers figured out how to grow what he called mini-guts from a single stem cell. These tiny, hollow spheres of intestinal tissue that kept renewing themselves, just like the real intestinal lining does. And from there, the organoid field exploded. By the mid-2000s, researchers around the world were growing organoids for nearly every major organ. Now, organoids aren't perfect models. They're small, typically a few millimeters at most. They lack blood vessels, which means the cells in the center often don't get enough oxygen and nutrients. They lack immune cells, nerves, the mechanical forces that real organs experience. But they capture something that flat cell cultures completely miss: the three-dimensional organization, the cell-cell interactions, the spatial patterning that makes an organ rather than just a bag of cells. And when you combine organoids with organ-on-a-chip technology, when you put organoids into microfluidic devices that provide flow, mechanical stimulation, and connections to other tissue types, you start to get something that's more than either approach alone. This convergence is sometimes called microphysiological systems, which is a mouthful, but it captures the idea: tiny systems that recapitulate human physiology. And the pharmaceutical industry has started paying very serious attention, because the potential to reduce drug development costs and timelines is enormous. We're talking about an industry that currently spends, on average, over $1 billion and 10 to 15 years to bring a single new drug to market. If microphysiological systems could even modestly improve the prediction of which drug candidates will work in humans and which won't, the savings would be measured in billions. But there's another application of all this technology that's perhaps even more profound, and it's one that connects back to something we touched on earlier: the idea of personalized medicine. Because if you can build a miniature version of a patient's organ from their own iPSCs, you don't just have a research tool. You have a way to practice medicine on that specific patient's biology before you ever treat the patient themselves. Imagine you're diagnosed with a particular type of cancer. Your doctor takes a blood sample, reprograms some of your cells into iPSCs, differentiates them into the relevant tissue type, and grows organoids that carry your exact genetic profile. Then they test a panel of chemotherapy drugs on those organoids to see which one your tumor is most sensitive to, and which ones your healthy tissue tolerates best. Instead of the current approach, which often involves trying a drug, waiting weeks to see if it works, switching to another drug if it doesn't, you could potentially identify the optimal treatment before the first dose. This isn't entirely hypothetical. Groups in the Netherlands, the United States, and elsewhere have been running clinical studies using patient-derived tumor organoids to guide cancer treatment decisions, with promising early results published in journals like Science in 2018 and beyond. The technology isn't yet fast enough or cheap enough for routine clinical use, but the trajectory is clear. And all of this, the organs on chips, the organoids, the iPSC-derived disease models, the personalized drug testing, it represents a fundamental shift in how we think about biomedical engineering's relationship to medicine. For most of the history we've been tracing together, the field was primarily about building things to put into the body: implants, prosthetics, artificial organs, scaffolds, physical objects designed to replace or repair damaged structures. And that work continues and remains vital. But increasingly, biomedical engineering is also about building things that stay outside the body: tiny biological models that let us understand disease, test treatments, and make better decisions without ever touching the patient. The body as something to be studied and modeled, not just fixed. Which brings us to a question that's been hovering in the background of everything we've discussed tonight. And it's a question that the field is grappling with right now, in real time, in ways that are both exciting and genuinely unsettling. It's the question of what happens when the tools we've been building start to converge, when you can reprogram a patient's cells, print living tissue, edit genes with precision, and model entire organ systems on a chip, and you put all of those capabilities together in the same room, in the same lab, in the same treatment plan. What happens when the line between understanding the body and redesigning it gets so thin that you can barely see it anymore? Because that's where we are now. That's the frontier. Let's start with the gene editing piece, because it ties everything together in a way that's both elegant and a little breathtaking. We've talked about iPSCs, taking a patient's skin cell or blood cell, reprogramming it back to a pluripotent state, and then coaxing it forward into whatever cell type you need: liver cells, retinal cells, neurons, heart muscle. That alone is extraordinary. But here's what makes it truly transformative. What if, before you differentiate those cells into the tissue you want, you fix a genetic defect first? This is where CRISPR-Cas9 enters the story. You've probably heard the name. It's been in the news enough. But let's talk about what it actually is, because the mechanism is beautiful in its simplicity. CRISPR stands for Clustered Regularly Interspaced Short Palindromic Repeats, which is a mouthful, but the concept is borrowed directly from bacteria. Bacteria have been fighting viruses for billions of years, and somewhere along the way, they evolved a kind of immune memory system. When a bacterium survives a viral attack, it stores a small snippet of the virus's DNA in its own genome, filed between those repeating palindromic sequences. If the same virus shows up again, the bacterium uses that stored snippet as a guide. It makes a small RNA copy that matches the viral DNA, attaches it to a protein called Cas9, and sends that complex out to find and cut the matching sequence. Scissors guided by a molecular GPS. In 2012, Jennifer Doudna at UC Berkeley and Emmanuel Charpentier, then at Umeå University in Sweden, published a landmark paper in Science showing that this bacterial system could be repurposed. You could design a synthetic guide, RNA, to match essentially any DNA sequence you wanted, pair it with Cas9, and cut the genome at precisely that location. Once cut, the cell's own repair machinery kicks in, and depending on how you manage that repair process, you can disable a gene, correct a mutation, or even insert new genetic material. Doudna and Charpentier shared the Nobel Prize in Chemistry in 2020 for this work, and the speed at which CRISPR moved from discovery to application was unlike anything the field had seen before. Now, think about what this means when you combine it with iPSC technology. Say a patient has sickle cell disease, a condition caused by a single point mutation in the gene for hemoglobin. One wrong letter in the DNA code, and the hemoglobin protein folds slightly differently, causing red blood cells to deform into that characteristic crescent shape. Those misshapen cells clog small blood vessels, cause excruciating pain crises, damage organs over time. It's a devastating disease, and it disproportionately affects people of African descent. For decades, the only cure was a bone marrow transplant from a matched donor, which carries its own serious risks and isn't available to most patients. But in December 2023, the FDA approved a therapy called Casgevy, developed by Vertex Pharmaceuticals and CRISPR Therapeutics, that uses CRISPR to edit a patient's own blood stem cells. They take the cells out, use CRISPR to modify a gene that reactivates fetal hemoglobin production, a form of hemoglobin that doesn't sickle, and then infuse the edited cells back into the patient. The first patient treated in a clinical trial, a woman named Victoria Gray in Nashville, Tennessee, received her edited cells in 2019 and has been essentially free of pain crises since. Think about that for a second. A disease that has caused suffering for millennia, traced to a single genetic letter, corrected by a tool borrowed from bacteria. And this is just the beginning of the convergence. Because CRISPR doesn't only work on blood cells. You can apply it to iPSCs before differentiating them into any tissue type. Imagine a patient with a genetic form of heart disease, hypertrophic cardiomyopathy, say, caused by a mutation in a gene encoding a cardiac muscle protein. You could take that patient's skin cells, reprogram them into iPSCs, use CRISPR to correct the mutation, differentiate the corrected iPSCs into heart muscle cells, and then, here's where the tissue engineering comes in, seed those cells onto a scaffold or bioprint them into a patch that you graft onto the damaged heart. Every technology we've discussed tonight, from Langer's biomaterials to Yamanaka's reprogramming to Ingber's microfluidic insights, feeding into a single therapeutic pipeline. We're not there yet for most organs. Let me be honest about that. The heart patch scenario I just described is being actively researched. Groups in Japan, Germany, and the United States are running early clinical trials with iPSC-derived cardiac patches, but it's still early days. The vascularization problem we talked about hasn't been fully solved. Getting those patches to integrate with the heart's existing electrical conduction system is fiendishly difficult, and the immune system, even when the cells carry the patient's own genetic profile, can sometimes react to the reprogramming process itself in ways we don't completely understand. But the trajectory, the direction of travel, is unmistakable, and it raises questions that aren't purely technical. Here's one that keeps bioethicists up at night, and it's worth sitting with for a moment. Everything I've described so far involves somatic gene editing, changes made to a patient's body cells that affect only that patient. Victoria Gray's edited blood stem cells will not pass their modifications to her children. The edit begins and ends with her, but CRISPR can also be used on germline cells, eggs, sperm, or embryos, where any changes would be inherited by all future generations. And in November 2018, a Chinese researcher named He Jiankuai announced that he had done exactly that. He had used CRISPR to edit the CCR5 gene in human embryos, attempting to confer resistance to HIV, and those embryos had been implanted and carried to term. Twin girls, known by the pseudonyms Lulu and Nana, were born with edited genomes. The scientific community's reaction was immediate and overwhelmingly negative, not because germline editing is inherently impossible or even because the goal of HIV resistance was unreasonable, but because the work was premature, the consent process was deeply flawed, the editing was imprecise, there were off-target mutations, and the long-term consequences for those children and their potential descendants were completely unknown. He Jiankui was sentenced to 3 years in prison by a Chinese court. But the genie, as they say, was out of the bottle. The question was no longer whether germline editing could be done, but who gets to decide when it should be done, and for what purposes, and with what safeguards. This is biomedical engineering's deepest ethical territory, and I bring it up not to alarm you, but because it's inseparable from the technical story we've been following all night. Every advance we've traced, from Harold Ridley noticing that PMMA didn't cause inflammation, to Robert Langer proving that polymers could release drugs on schedule, to Shinya Yamanaka discovering that 4 transcription factors could rewind cellular time. Every one of those breakthroughs expanded the boundary of what's possible. And each time the boundary moved, society had to figure out where the new limits should be. Not the limits of what we can do, but the limits of what we should do. Biomedical engineering has always been a conversation between capability and responsibility, and that conversation is getting more complex, not less. But here's the thing, and this is what I find genuinely comforting about this field, having spent all this time walking through its history with you. The conversation is happening. It's messy and contentious, and sometimes frustratingly slow, but it's happening. The FDA Modernization Act of 2022, which we talked about earlier, didn't just appear out of nowhere. It was the product of decades of advocacy, research, ethical debate, and regulatory evolution. The guidelines around iPSC clinical trials, the oversight frameworks for gene therapy, the international moratoriums on germline editing. These are all evidence that the engineering community and the broader society are trying, genuinely trying, to get this right. And meanwhile, the quieter work continues. Somewhere tonight, a graduate student is troubleshooting a bioprinter, trying to get the nozzle diameter just right so that hepatocytes survive the printing process. Somewhere, a surgeon is implanting a tissue-engineered trachea in a child born with a defective airway. Somewhere, a pharmaceutical company is running drug candidates through a panel of organs on chips, catching a liver toxicity signal that would have been missed by animal testing and might have harmed people in a clinical trial. Somewhere, a cancer patient's tumor organoids are sitting in a multi-well plate, being exposed to 8 different chemotherapy regimens, and tomorrow morning, an oncologist will look at the results and have a better idea of which treatment to recommend. These aren't dramatic headlines. They're the slow, steady accumulation of capability that defines engineering at its best. Remember how we started tonight, talking about the ancient Egyptians using wooden toes, and the long centuries where the body was essentially a black box that you could splint and stitch but never truly repair from the inside? Think about the distance from there to here. From a carved wooden toe strapped to a foot with leather thongs, to a living patch of heart muscle grown from a patient's own reprogrammed skin cells, seated onto a biodegradable scaffold with a corrected genetic mutation, tested first on a personalized organ on a chip. That arc, that long, winding, sometimes stumbling, often brilliant arc, is the story of biomedical engineering. And it's still being written. That's maybe the most important thing. We're not at the end of this story. We're not even close. The tools are converging, the understanding is deepening, and the questions are getting harder and more fascinating. Artificial wombs for extremely premature infants, neural interfaces that let paralyzed patients control robotic limbs with their thoughts. Xenotransplantation, genetically modified pig organs for human transplant, which had its first landmark case in January 2022, when surgeons at the University of Maryland transplanted a CRISPR-edited pig heart into David Bennett, a patient with terminal heart disease. He survived for 2 months, and while the outcome was ultimately tragic, the fact that a pig heart functioned in a human body at all, even briefly, was a proof of concept that would have seemed like science fiction a generation ago. All of these threads are still unspooling, and the people pulling on them are, by and large, the same kind of people we've met all night: curious, stubborn, occasionally reckless, often brilliant, always driven by that fundamental engineering impulse. This thing is broken, and I think I can figure out how to fix it. So as you lie there, maybe, drifting now, maybe already asleep, and if you are, that's perfectly fine. That was always the deal. I want you to hold on to one thought. Your body, right now, is doing 1,000 things that biomedical engineers have spent centuries trying to understand and replicate. Your heart is beating with an electrical rhythm that no artificial device has fully matched. Your immune system is patrolling for threats with a sophistication that makes the most advanced biosensor look like a toy. Your cells are dividing, differentiating, repairing, communicating in a symphony of molecular signals that we've only begun to decode. You are, in the most literal sense, the most extraordinary piece of engineering in the known universe. And the story of biomedical engineering is really just the story of people trying to understand that, trying to learn from it, to support it when it falters, and maybe, gently, carefully, to improve on it when they can. It's a good story. And it's yours now, too. Let it settle somewhere comfortable, and let yourself rest. The engineers will still be at it in the morning.